that it has a basis. This basis consists of a finite number of vectors. Then all of these bases have the same size. Okay? So if, for example, if a vector space has a basis which consists of 10 vectors, then if you find other bases for the same vector space V, then all the bases has 10 vectors. Okay. So that this is an important property because we always have a question that is it possible for a vector space to have bases with different number of vectors? So, but for vector space having a finite basis, then the question is that all the bases have the same number of vectors. Alright, so before that we recall theorem 2.4.10. Right, so 2.4.10 states that every set of more than n vectors in the span of a subset of size n in a vector space is linearly dependent. So the situation is here. So this is the vector space. This is the span of a set, say U1, U2, U2, U3. Okay, so we have U1, U2, U3, U3. Okay, so we have a set of n vectors, right, in the vector space, and it spans to this subspace. Now, in the span, if we pick up more than n vectors, so say we pick up say V1, V2, Vm, such as m greater than n. Okay, so we have a set of more than n vectors. Then V1, V2, up to Vm. Okay, this one is linearly dependent. Okay, so that is the meaning of theorem 2.4.10. Okay, it's a theorem we have proved before. All right, so now, so let B be a finite basis for V. Right? So the B is a finite basis for V, and let C be another basis. Our purpose is to prove that the size of C is the same as size of B. This is our purpose. Any questions up to now? Or the statement? Alright. Since every element of the basis C is in V, which is the span of V. Okay. As a basis, the vector space is the span of V. So if C has more than okay. With the size of B equal to n. Right. So maybe I will fix that. The size of B is equal to n. So if C has more than n vectors, or more than n elements, C must be linearly dependent. Okay? So if C is more than an element, C must be linearly dependent. A contradiction. Okay? Because C is linearly independent as a basis. So that's the contradiction to the linear independency. Of C. So that's the size of C would be less than equal to the size of B. Alright, so now we know C has finite, it's a finite set. It's a finite set. Okay? Now, similarly, since C spans V and B is linearly independent. So the size of B is less than or equal to the size of C. By applying the same theorem. Okay? Because now we already know C is a finite set, so it has a finite number of elements. And the span V. Okay. So that V equal to C. Maybe I'll set it up. So V is equal to C. Okay, so a vector space we having a finite basis is said to be finite dimensional. Alright, and in this case, the size of any basis for V, okay, it's called the dimension of V, and denote it as DIM. So now we are able to introduce the concept of dimension of vector space. Okay. Because the previous theorem says that if a vector space V has a finite basis, then all the bases have the same number of vectors. So that we can define the common size as the dimension of the vector space V. Okay. And then this vector space will be called finite dimensional vector space. Now, if we consider two finite dimensional vector space, and the two finite dimensional vector spaces are isomorphic. If and only if their dimension okay, so their dimensions are the same. So now it's easy to justify whether two finite dimensional vector space to be isomorphic to each other. The if and only condition is their dimensions are the same. So if two finite dimensional vector space have the same dimension, then these two vector spaces are isomorphic. If they have different dimensions, then these two finite dimensional vector spaces are not isomorphic. All right. So to establish, we say two vector spaces are isomorphic. Then we just construct an isomorphism from one vector space to another vector space. Right? So this is our approach to establish an isomorphism. An isomorphism means a bijective linear transformation. Okay. Alright, so we go this direction. So the direction is that their dimensions are the same. Right? So suppose they have the same dimension. So let V V1 up to Vn, and the C from 1, from 2 up to n, be basis for vector spaces V and W respectively. Okay. So we have a basis B for vector space V, basis C for vector space W, and because we assume they have the same dimension, so the number of elements in all spaces are the same. V1, V2, Vn for B, W1, W2 up to Wn for C. So we have. Now, by theorem 2.4.12 in chapter 2, there is a unique linear transformation T from V to W such that we assign for each element in B. Right? So this B is linearly independent and span the vector space V. So that we assign them to here. So we give a specification that for every element in the basis B, we assign Wi for that. Okay? And such a linear transformation exists and unique by theorem 2.4.12. Okay? We proved that before in chapter 2. So this T is uniquely determined. And there exists, again, is a unique linear transformation S from W to V such that S Wi equal to Vi for all I. And because Wi form a basis, so C is linearly independent and span the vector space W. So this assignment gives you a unique linear transformation. Okay, they are all from theorem 2.4.12. All right, so now we look at the composition. So now you will compose S compose T, then operate on Vi. Then we find that S T Vi. But TVI is WI, so SWI. But SWI is VI. Okay? So the composition of S and T send the VI to VI. And also, alright, so there is a unique by theorem, and also let's say we have that, right? And also identity ID V equal to VI. Okay. So identity mapping is also map VI to VI, of course, right? So and then so by theorem 2.4.12, assignment for VI to VI give us a unique linear transformation, right? So we must have the S and the T equal to identity of V. Must be equal because we have a unique linear transformation from V to V. Okay, so that this must be identity. Similarly, T on S of I okay, Wi. So this composition send Wi to Wi, and also identity of W send Wi to Wi. So they have the same specification. So this composition send Wi to Wi, and the identity function send Wi to Wi. So again, by theorem 4.4.7, P of S is the identity of W. Okay, so we have this one is identity. So P is invertible. It's an invertible function with the inverse S. Okay? And by theorem 5.2.8, I would prove that T is bijective linear transformation. i.e. an isomorphism. So thus V is isomorphic to W. Okay, so we put the backward direction. So if two vector spaces have the same dimension, then they are isomorphic. Okay, so we prove that by the construction of an isomorphism. Okay, so you can see that we all apply theorem 2.4.12. Okay, specify the image for vectors in a basis, give us a unique linear transformation. Okay, so we have that. Now we are going to prove the forward direction. Now, since the two finite dimensional vector spaces, V and the W are isomorphic, to each other, So there is an isomorphism T from V to W. Okay, we have an isomorphism. Now we let B be a basis. Be a basis for the domain V. Right? So let B is the basis for the domain V. Now we consider C is the set of all images. Okay, so that C consists of the images of V1, V2 up to Vn in W in the codomain. Alright, so which is a subset of the codomain. Now we want to prove that C is a basis for W. Right? So the first claim that the W is the span of C. Okay. All right? Sorry. So things T is untrue because T is isomorphic. Isomorphic means a bijective linear transformation. So T is untrue for each W in the codomain. There exists a V in the domain such that TV equal to W, right? This is untrue. So every element in the codomain is the image of an element in the domain. Here. All right. Now, since V is equal to alpha 1 V1 plus alpha 2 V2 plus alpha n Vn for some alpha 1, alpha n, some scalars. Right? And because B is a basis, right? So we have that, and the T is linear. Okay, this T is linear. We have W equal to TV. So T is alpha 1 V1 plus alpha 2 V2 plus plus alpha n Vn. Okay, so B is a linear combination of the elements in B. So we have that, and the bilinearity we have alpha 1 T V1 plus alpha 2 T V2 plus plus alpha n T Vn. So you can see that W is in the span of C. Okay? So you see that for each W with vector in the codomain, the W is in span C. So that W is a subset of the span C. Okay? So this implies that W is equal to the span of C. So we prove the claim first. The second claim, that C is linearly independent. Okay? Consider an arbitrary linear relation on the set C. So it's alpha 1t v1 plus alpha 2t v2 plus plus alpha n t vn equal to 0. Okay? So this is an arbitrary linear relation. Okay? So we have that. And that means that t alpha 1 v1 plus alpha 2 v2 plus plus alpha n vn equal to 0. Since t is linear. And now this implies that alpha 1 v1 plus alpha 2 v2 plus alpha n vn equal to the 0 vector. Since t is 1 to 1, i.e. a linear transformation is 1 to 1 if and only if the kernel of t is just a 0 vector. Okay? We put the lemma, right? The lemma. So that the only possible vector in the domain have image equal to 0 is that is 0. Alright? So we have a linear relation on the set B. But B is linearly independent. So this implies that alpha 1 equal to alpha 2 equal to alpha n equal to 0. Since B is linearly independent. Alright, so if we have an arbitrary linear relation on C, we find that the coefficient must be all 0. So C should be linearly independent. So of course, so that C is linearly independent, of course. Okay. So with these two claims, we know so we conclude that C is a basis for the codomain. Right? C is a basis for codomain. Okay, so dimension of W is equal to the size of C. Because we have a basis, and this basis is finite because C has only n elements. So C, but C has the size as B, right? Because you can see the one-to-one correspondence. They are images of the vectors in the basis B. And this is dimension of the group. Okay, and so they have the same dimension. Okay, now the next theorem, 5.2.8, is about removing an element. Now let S be a subset of a vector space V, and the let V is an element in the set S, be a linear combination of other elements in S. Then the span of S is equal to the span of S back. You just delete the element V from S. So it's called removing an element without change the span of the set. I think I have proved the theorem before. So but the version is for Euclidean spaces. Or at least in some exercise, or I think it is an exercise before. Anyway, so from as an exercise, all right. So that it's just that this theorem is useful when we deal with a finite subset of a vector space. So if we find an element, a vector in this finite subset, which is a linear combination of the other elements in X, then we can remove the vector from S without changing its span. So it's called a downsize theorem. Okay, so that so the proof actually, I think we deal with such a problem before in an exercise. Okay. Right. So now an application of theorem 5.2.8 is here. If a set S of n vectors, right? Suppose we have a set of n vectors spans and n dimensional vector space with. Okay, so it's very interesting. First, we have a vector space which is n dimensional, so we know the dimension of the vector space n, and we know a set. All right, the set consists of n vectors and the span the v. Then S is a basis for V. means that in the situation x is a linearly independent set. Okay? So if S span the vector space V, and the size of X is equal to the dimension of V, then this set also linearly independent, and then V is a basis, and then a basis for V. Okay, so it's very interesting. So it's a way to find a basis. Okay. So if you know a vector space is n-dimensional, and then you find a set with n elements, span the V, then S must be a basis. You don't need to check the S is linearly independent because it's automatically true. Okay, so that is the way we have. Now, suppose we prove it by contradiction. Suppose S equal to U1, U2 up to UN is linearly dependent. So S span V and S, the size of X is the same as the dimension of the vector space. And we suppose S is linearly dependent. Okay, and we want to show a contradiction. Okay, then there is a non-trivial linear relation on S. E. And E on alpha 1, U1 plus alpha 2, U2 plus alpha n equal to 0, V. With at least one of alpha 1 up to alpha n to be non-zero. So it says alpha I not equal to 0. Okay. So then Ui becomes to minus alpha 1 alpha I, U1 plus plus minus alpha I minus 1 alpha I, U I minus 1 plus minus alpha I plus 1 alpha I, U I plus 1 plus minus alpha n alpha I, Ui. Okay, so we can move Ui to the other side. So we can express Ui as a linear combination. Alright, what's that? So the span of S, you can remove Ui from the basis, from the set S, okay? So this is the set, which is V, by theorem 5.2.8. Okay, so from the theorem, we can remove one element out. Okay, now since any basis C for V must be linearly independent. C must be less than the size. Okay. By theorem 2.4.10. Remember, theorem 2.4.10 says that if you have a spanning set, okay, and the size, for example, here this is n-1, right? If we have more than element, more than this, there must be dependent. That is yeah. So if the C is basically a set, if the size of C is greater than the spanning set, then this set must be linearly dependent. Okay. So that the size of C cannot greater than the size of the spanning set. Okay. This is n-1. Okay. So if so that because any base is linearly independent, so the size must be less than n-1. Otherwise, C becomes too linearly dependent from the theorem here. So and then the dimension of V is equal to the size will be less than or equal to 1. So this is a contradiction to the dimension of V is equal to n. Okay. So this is contradiction. So the assumption here that S is linearly dependent give us a contradiction to the dimension of V is equal to n, so that S must be linearly independent. And then a basis for V. Okay. Okay, so let's take 5 minutes for break. Okay, so the theorem here is that to find a basis for n-dimensional vector space, you just find a spanning set with n elements. The other direction, 5.2.10, the other direction is that in an n-dimensional vector space, we on every linearly independent set of n vectors, is a basis for V. Right, so this time is that to find a basis for n-dimensional vector space, we just find a linear independent set which has n vectors. Okay, so you can compare these two theorems here and there. Now, a proof here. We prove this by contradiction again. So suppose S does not span with, right? So suppose S does not span. Okay? Then we can pick up a vector V in the rest of the space. Okay, so here is the situation. V is here, and this is the span of S here, and we have an vector V outside of the span. Because S does not span V, means that the span of X is a proper subset of V. So we can pick up a vector V in here. Alright, what's that? And then the union S and the V. Right, so the new set is linearly independent. By a theorem in chapter 2, right? This is theorem 2.4.11. So in 2.4.11, it just describes this situation. The theorem tells us how to find a linearly independent set. Right? Remember that? First of all, we pick up a point, a vector, non-zero vector from vector space, and form the span of the vector space. Outside the span, we pick up another one, we call V2. Right? Now we have V1, V2 linearly independent, right? And form its span. If the span of V1, V2 is not V, then we pick up the third one, V3. Join to V1, V2. And V1, V2, V3 becomes to a bigger linearly independent set. Okay? Right? And bigger, bigger, and bigger, and bigger, up to where? Up to the span of the set equal to the V. And we have no other possibility to pick up element. So that this is the way, the situation. Right? Alright? So now we have a bigger linearly independent set. Now since dimension of V is equal to n, right, there exists a basis V of size and for V, right, because it's basis. Now since it's in the span of V. Okay? In the span of, and the size, which is n plus 1, is bigger than the size of V. So the union must be linearly dependent. Right? By theorem 2.4.10 again. Because that B is a spanning set and the size of B is n, and this set has more elements than the spanning set B. So by the theorem, this set must be linearly dependent. So it's a contradiction to our construction here. So you get a contradiction. Okay? And we get contradiction because we assume S does not span with it. So the only way we can have is that S span with. And then basis. And then it's a basis for it. Okay? All right. Next theorem. If a set of n vectors, all right, span a vector space, all right. So if we know, we can find a spanning set for vector space V, and this spanning set has n elements. Then the dimension of V is an upper bound, which is n. Okay. By theorem 2.4.10, we cannot V is the span of S, right? As the span of S cannot have a linearly independent subset of size greater than n. Okay? Because the set is the spanning set has only n elements. So in the span of S, you pick up a subset. If the subset size greater than n, then must be linearly dependent. All right, must be linear by theorem 2.4.10. Right. Okay, so that's V is finite dimensional. So that's the size of a basis or of any basis for V must be less than or equal to n. Because any basis for V must be linearly independent, so that the basis cannot have size greater than n. Because if a basis has size greater than n, then we have a linearly independent set of size greater than n. This is impossible from theorem 2.4. Okay. So the size of any basis for V must be less than or equal to n, and therefore V is finite dimensional. And the dimension I should use the capital D. Dimension of V is less than or equal to n. So n comes to an upper bound. If we have a spanning set of the spanning set of size n. Okay, and now we have a corresponding theorem about linear another way round. So if there is a linearly independent set of n vectors in a vector space, then either V is infinite dimensional, or the dimension of V is greater than or equal to n. So n comes to a low bound. If we have a linearly independent set of n vectors in a vector space, right? So if V is infinite dimensional, then we have nothing to say. So we are considering, so we only consider the case that V is finite dimensional. Okay? V is finite dimensional. Okay, so now let S be such a linearly independent set of n vectors V. Right? So suppose it's such a set. Now suppose that the dimension of V is less than n. Less than is the other option, right? The opposite of this inequality. So now suppose we have that. Okay, so there exists. So now there is a basis B for V with the size of B is equal to the dimension of V, and which is less than n. Now, since the set X is contained in V, the span of B, because V is the basis, so this linearly independent set is contained in the span of B, and the size of Xn is greater than the size of B, which is the dimension of V. Okay? So S is linearly dependent. Again, by theorem 2.4.10. Right, so again, by theorem 2.4.10, that S is linearly dependent. Okay, so that is a contradiction, because that the set X is linearly independent by construction. Yeah. So we got a contradiction. So that the dimension of V should be greater than equal to n. So it seems that we use the theorem, we use theorem 2.4.10 a lot. Okay. And a very good application is here. So we will see very good application to the common space of the matrix. (5.2.13). The pivot columns of a matrix A form a basis for the common space of A. Okay, so now a very good application. Okay. Proof. All right, so let U be the reduced row echelon form. Of A. Okay, so for example, A has say okay, suppose we have a 4 times 6 matrix, and so it has 6 columns here. And the reduced row echelon form, you like this one. So you see that the pivot, we have pivot in the 2nd column, pivot in the 4th column, and a pivot in the 6th column. So this is 3 are people columns. Okay? These are people columns. Okay. So, all right. So, look at here. So they are this. Okay, and things that ax equals 0 if and only if ux equals 0. Okay. Because that they will have the same kernel, so ax 0 is the same as, so the solution set. So any solution, right, for ax equals 0, if and only if ux equals 0. Okay, and so that so the corresponding that so alpha A2, for example, plus beta A4 plus gamma A6 equal to 0, right? If and only if alpha E1 plus beta E2 plus gamma E3 equal to 0. Okay? So this is the standard basis. So if we have a linear relation for the columns of A, we have a corresponding linear relation for the columns of the U, because they have the same solution set. So the kernel of A is equal to the kernel of U. Okay? So that is the situation. Okay? Now, because E1, E2, E3, they are standard unit vectors, so they are linearly independent. E1, E2, E3 are linearly independent. So any linear relation should have 0 coefficient. Okay? Now, you have linear relation, corresponding linear relation here, right? And because alpha, beta, gamma are all equal to 0, so A2, A4, A6 must be linearly independent. Is that okay? So this shows that people columns are linearly independent. From this example. Okay, so far. Let's just pick up the coefficient of A1 is 0, A3 is 0, A4, A5 is 0. I just form such a linear relation. And we have corresponding linear relation here. Okay? Right? So this is a linear relation. Okay? So a linear relation on the columns of A, say x1, x1 plus x2, x2 plus xn, xn equal to 0. Right, so this is equal to ax equal to 0. Right? Correspond. So a linear relation corresponds to a linear relation on columns of U. x1, u1 plus x2, u2 plus etc. plus xn, un equal to 0. So this is corresponding to u x equal to 0. Right? So with the same coefficients, x1, x2, up to xn. Okay, so we have this correspondence among linear relations. Now, since pivot columns in U form a linearly since pivot column are standard distinct standard unit vectors in Rm. Okay. So A is that means the dimension is m times n. So the pivot columns here, you can see the pivot columns in the reduced direction form must be standard unit vectors. Okay. So the pivot columns distinct standard unit vectors and form a linearly dependent set. Right? So the corresponding pivot columns in A form also form a linearly independent set. Okay? Okay? So that because they have the same linear relations, corresponding linear relations. Okay. Up to now, up here, any questions? So we have this one. Right. So the pivot columns from linear equivalent state. Now, and non-pivot columns are linear combinations of pivot columns. U. Okay? You can see non-pivot columns must be linear combination of the pivot columns. Why? For example, this all zero, no problem, right? It's a trivial linear combination of E1, E2, E3. How about this one? This one has only possible non-zero entries, so this one is a linear combination of E1. Okay? How about these two? These two arbitrary entries is a linear combination of this one and this one, because they can find the pivot there. The others must be zero. So every non-zero non-pivot column must be a linear combination of the standard unit vector. Is that okay? It's very easy to see from here. So non-pivot columns are linear combination of pivot columns in U. That's so pivot column and non-pivot column and the pivot column, they can form a linear relation, because when they can be expressed as linear combination, then they will form a linear relation. So that's non-pivot columns are linear combination of pivot column in A. So by the removing theorem, removing an element theorem, which is all right, here 5.2.8, removing an element the span. So the common space of A is the span of A1, A2, AN. We come to the span of pivot column of A. Okay? Because every non-pivot column is a linear combination of pivot columns, so they can be removed from the spanning set. one by one. Alright, so by theorem 5.2.8, we can remove rows non-pivot columns. Alright, and find the set so that this will become to a spanning set. Okay. So it's the set of all pivot columns of A is the spanning set of the column space. And we already show that this set is linearly independent. So the pivot columns of A, alright, it's a basis for column A. And we're back. So the important thing is this observation that any linear relation on the columns of A is a corresponding linear relation on the columns of the reduced low echelon form. This is crucial. Okay, for this example, you can see that. All right, so from that we can show the pivot columns. The pivot columns in U, because they are standard unit vectors, so they form linearly independent set. So the corresponding pivot columns in A also form linearly independent set. So that is from here. And from the reduced low echelon form, every non-pivot column is a linear combination of pivot columns. So that correspondingly, every non-pivot columns in A is a linear combination of pivot columns in A. So that's shown by theorem, by the removing an element theorem, that the spanning set, in the spanning set we can remove all non-pivot columns without changing the spanning set. Okay, and so finally we prove that the set of all pivot columns of A is a basis. Questions? Alright, so these are very good applications to matrix, to column spaces of matrices. Okay, so let T be a linear transformation from an n-dimensional vector space V to a vector space W. Alright, so the domain of the linear transformation has finite dimension, and the dimension is n. Okay, but W may be infinite dimensional. We don't know, just a vector space. Then the dimension of the range of T will be less than or equal to the dimension of V. Okay, so the range of the linear transformation T has dimension less than or equal to the dimension of the domain. Okay, so let B to be V1, V2, Vn be a basis for V. Okay? Then the range Tb it's by definition is the image of all vectors in the domain. Okay? And that is alpha 1 V1 plus alpha 2 V2 plus delta plus alpha n Vn. Okay? So every element in the domain V is a linear combination of the vectors in basis V. Okay. So that by linearity of T, we have alpha 1 T V1 plus delta plus alpha n T Vn given alpha 1 delta are scalars. So what is that? This is the span of the set T V1 T Vn. Okay, so the range is spanned by a set of vector, right? The most vectors. Okay. Now, so by our theorem, by theorem 5.2.11. Right, 5.11, the dimension of TV, the range, will be less than or equal to the set of the set of the set. But the set of the set is less than or equal to n. Okay. Why? Because it's possible that TV1 equal to TV2, right? So you may have a repetition. So the size of this set may be less than or equal to n. And this is dimension of V. Okay, so we get the proof. So it's a direct application of theorem 5.2.11. Theorem 5.2.11 actually is equal to theorem 5.4.12. Okay, so I don't need to state it again. 16. Any linearly independent set S in a finite dimensional vector space V can be extended to a basis for V. I think the proof is adding an element theorem. So the proof is here. The situation is here. This is V. Okay? And this is the span of the S. Okay? So the situation is here. This is span of S. And S is the linearly independent set. Alright, so now if the span of S is equal to V, right? S is a linearly independent set. Now, if the span of S is equal to V, then S is a basis already. Okay, so we have that, right? If the span of S is not equal to V, just like this situation, then we pick up. Then we pick up a vector V. So we let dimension of V is equal to n, and the set of F is equal to K. Alright? So I have to suppose the dimension of V is n, because it's finite dimension, so it's n, and the size of the linear independent set is K. Alright? Now, okay, maybe I will multiply it. Then by theorem, five to 2.12. I already erased that. K, the side, the K, which must be, is the lower bound of the dimension. Okay. So K must be less than or equal to n. Okay. So this is the theorem we just proved. Alright, so if K equal to n, then if K equal to n, then S is a basis for V. Again, by theorem, I think the theorem is 5.2.10. If we find a linear independent set, its size is the same as the dimension of V, then this linear independent set is a basis. Okay, so we just apply the previous theorem. Now, if K is less than n, then of course, then the span in set is not equal to, right? So it cannot span V. We pick up, so we pick up a vector, say V K plus 1 in the difference. So we have here V K plus 1, and here we have V, for example, V1 into VK. Okay. So now the situation is that the span set is not equal to V, so we pick up VK plus 1 in V and minus the span of X. And now X union of VK plus 1, alright, is a linearly independent set. Alright, in V by, again by theorem 2.4 I think it's 10. Yeah, I think it's 10. Oh, 11, sorry. 11, yeah? Okay, so we grow the linear independent set by 1. Now, if k plus 1 is less than n, right, we continue extending, right, the resulted linearly independent set. By adding vectors 1 by 1 until a linearly independent set S union Vk plus 1, Vk plus 2 up to Vn is obtained. With the size of this union equal to n, then this set is a basis for V, again by theorem 5.2. Okay. So the idea is it's very simple. Every time you pick up a vector outside the span, so if the span is not equal to V, then you will add vectors 1 by 1. Okay, up to the size of the linear independent set come to n. When the size of the linear independent set come to n, and n is equal to the dimension of the big space, then by theorem 5.2.10, that this newly established set come to a basis. Okay, I think I have I leave the last one and a very important theorem, the rank nullity theorem, to next week. I can't finish section 5.2. It's a long section, and okay, so well. I think I have to start here. Any questions? All right, no questions. I will see you next week.